So today we're looking at 7.2 absolute value functions. I've left the warm-up for you to finish on your own. It should be doable after having watched the 7.1 video. So let's jump right into it. We're going to investigate some absolute value functions. So we're going to compare linear functions with corresponding absolute value functions. So consider these two functions. F of x is just given as x. G of x is given as the absolute value of x. So let's compare using these values of x. If f of x is equal to x, then it will have all the same values, because you plug in this value for x, and that's what you get for f of x. So nothing changes here. Now, g of x is the absolute value of x. So we take the absolute value of -3, which is 3. The absolute value of -2, which is 2. And so on like that. The absolute value of all these positive numbers is also positive. So basically, what we have then for original linear function, we have points like that, and they make a line. There. And for our absolute value function, everything's positive. So when x is -3, y is 3. When x is -2, y is +2. -1 is 1, 0 is 0, and then over here we have all the same points as the other function. So what we end up with is a function where we only have positive values. So everything to the left is positive, everything to the right is positive. Because the absolute value represents a distance, you can't have negative values. So everything will be positive. So your blue function here is the absolute value, the graph of the absolute value. Okay. Leave you to answer these. I'm sure you guys can come up with something as a team. Use your textbook for help as well. Okay, so now we're going to look at quadratics and the absolute value of a quadratic function. So again, we're going to do the same thing. So plug in a few values. So -3 into f of x. So -3 would be -3 squared is 9, -3 is 6. -2 squared is 4, -3 is 1. -1 squared is 1, -3 is -2. 0 squared is 0, -3 is -3. 1 squared is 1, -3 is -2. 2 squared is 4, -3 is 1. And 3 squared is 9, -3 is 6. So you notice the symmetry about this point, right? -2, 1, 6, -2, 1, 6. Okay. Here, a little different. -3 squared is 9, -3 is 6. Absolute value of 6 is 6. Absolute value of 1 is 1. Absolute value of -2 is +2. Absolute value of -3 is +3. Absolute value of -2 is +2, and otherwise the values should be the same because it's the same function, except now the absolute value brackets around. So we're basically just getting all the same answers but putting hashes around them. So let's see what this looks like. -3 and 6 is up here. -2 and 1 is here. -1 and -2 is here. 0 and -3 is here. That's your vertex. 1 and negative 2 is here. And of course there's going to be symmetry. So that one will be there. And then this one will be there. And here is your quadratic function. Now, anything negative is not allowed in an absolute value function. So this part that's below the x-axis, this is the negative part. And you're going to see something interesting that happens with that when we plot it. So this point is the same, negative 3 and 6. This point is the same, negative 2 and 1. But now something interesting happens. We go to negative 1 and it becomes 2. So negative 1 and 2. And then 0 becomes 3 instead of negative 3. So it goes up like that. 1 becomes 2 instead of negative 2. So again, you have that symmetry there. And then we have 2 and 1, which is there, and 3 and 6, which is there. So basically, we've got the exact same curve until it almost becomes negative, then it changes its mind, goes up, but then the curve finishes out the exact same way as the other one. So only the part that would dip below the x-axis is reflected in the x-axis. So if you took a mirror and you put it right here, and kind of this was the reflective side here, this is where you'd see this thing. And you'll find that that's the exact same as if you did this here, right? If you took a mirror and put it on the x-axis again, then this line is a reflection of everything that was negative. It just becomes positive, and that's what absolute value does. So this is in the textbook. Function composed of two or more separate functions or pieces, each with its own domain, that combine to define the overall function are called piecewise functions. Okay, the absolute function y equals absolute value of x can be defined as a piecewise function where y equals x if x is greater than or equal to 0, and y equals negative x if x is less than or equal to 0. So if x is negative 3, for example, then y is negative of negative 3, which of course always leaves you with a positive number. Alright, so let's get some practice. I'm going to leave the other warm-up for you there on your page to do on your own. Consider the absolute value function y equals the absolute value of 2x minus 3. Determine the y-intercept and x-intercept. So y-intercept is when x equals 0. So we're going to have the point 0 and something. So let's plug it in. So when x equals 0, we have 0 minus 3, the absolute value of that. So the absolute value of negative 3 is 3. Okay, and the x-intercept is when y equals 0. So we're going to have something and 0. So you set your y equal to 0 equals the absolute value of 2x minus 3. Now this is where it gets a little interesting, because we have a couple possible scenarios. If 2x is greater than 3, then this is positive, and we take the positive of this thing and solve. So we would go 2x minus 3 equals 0, 3 equals 2x, and x equals 3 halves, or 1.5, if you like decimals. Alright, now the other scenario is that if 2x is less than 3, then what's inside here is going to be negative. So let's say x is 1. Then this is 2 times 1 is 2, minus 3 is negative 1. And then we take the negative of this whole thing in brackets. So it would be 0 equals the negative of 2x minus 3. And then we solve this one. 0 equals negative 2x plus 3. 2x equals 3, and x equals 3 halves. So we happen to get the exact same value here, which is nice. So we know that that is going to be our x-intercept. Sketch the graph. Okay. So here are our intercepts. You can just double check the work. Stop moving. Okay. There we go. So the graph now. Using a table of values is easy. We already have the x-intercept, we already have the y-intercept, and we can sketch the graph using a bunch of those points. Make a nice little table here just by plugging in a couple values to the left of your x-intercept and a couple values to the right of your x-intercept. Okay. This is what the graph will look like. So we just plug in a point like negative 1. Plug in negative 1, we get 2 times negative 1 is negative 1, or negative 2, sorry. Minus 3 is negative 5. Absolute value is 5. Notice that this column is always positive, okay? And we have symmetry about 0. All right? So that's where you have your symmetry. And it's just your regular absolute value function, but moved 3 halves to the right, or 1.5 to the right. So it says, since there's no x value that cannot be substituted into this function, the domain is all real numbers. So we're allowed to put any x whatsoever in here. You can put negative 2, you can put negative 2 million and 2, or positive 2 million and 2. It doesn't matter. Anything is possible. The range is only going to be positive numbers. It will never drop below 0 because we're always taking the absolute value of it. Okay? So it will always be greater than or equal to 0. Okay. So essentially the v-shape of this graph is composed of 2 separate linear functions. One would be the line that comes down like this, and the other would be the line that goes up like that. So it can be thought of as a piecewise function. Okay, so my buttons don't really want to work here very well. So to the right of the x-intercept, which is this value, so when x is greater than this value, so to the right on the graph, we use this function because inside the absolute value brackets is positive. So then whenever x is less than 3 halves, or 1.5, what you get in here is a negative number. And then when it's a negative number inside the absolute value brackets, we make it the negative of that number. So it gets written like this: y is the negative of whatever was inside the brackets. And then it looks like this: y equals negative 2x plus 3. Now this is just a regular line with slope of minus 2, right? mx plus b, and y-intercept of 3. So then we can combine the two linear functions to make a piecewise function. So we use the positive version of this function if x is greater than 3 halves, and we use the negative version of the function if x is less than 3 halves, because it becomes negative inside the absolute value brackets. And then we'll see what it looks like here in a sec. I hope. We'll try. Or not. Oh, we already looked at that one. Never mind. Seem to be having some trouble this morning. Okay. Here is your turn for you to go ahead and give a try. So determine your y-intercept by making x 0. Determine your x-intercept by making y 0 and solving. Sketch the graph. Now remember, this is just like a line, but wherever it would be negative, it just gets reflected in the x-axis, and those all become positive. So we don't have anything below the x-axis in this absolute value function. Okay, so your domain, whatever you're allowed to plug in for x, and your range, whatever the results are for y, and then express as a piecewise function. So hit pause, give it a try, and unpause, and the answer will be here. There you go. Okay, so here's another example, this time a quadratic. So start with the a, determine the y and x-intercepts. Determine the y-intercept by plugging in 0 for x. So the y-intercept would be, okay, 0 plus 0 plus 8. Which of course gives us the point 0 and 8 as our y-intercept. Now your x-intercept is going to be when y equals 0. So set y equal to 0, and then factor this statement. So this is the negative of x squared minus 2x minus 8. So your numbers are going to be minus 4 and positive 2. So x minus 4 times x plus 2 equals 0. So then your intercepts are 4 and 0 and minus 2 and 0. So sketching the graph of this thing opens down, and it has these intercepts at minus 2 and 0 and positive 4 and 0. So between minus 2 and positive 4, it's going to be above the x-axis, but then to the left of minus 2 and to the right of positive 4, it's going to be below the x-axis, but that's not allowed because it's the absolute value of that function. So we're going to take those parts that are below the x-axis and they'll get flipped up like that, and your graph is going to end up looking like kind of like a big W with the curved part in the center there. And this will be -2 and 0, and this will be +4 and 0. Okay, so let's go ahead and confirm. Oh, that's the x-intercepts. Okay. Okay, so this is converting it to vertex form. That just helps us locate the vertex. Of course, it opens down, and the vertex is a +1 and +9. And as I said before, nothing below the x-axis is allowed because it's the absolute value of this thing. So when we get to these intercepts, it has to reflect in the x-axis and come back up. So it's always like we put a mirror on the x-axis, and these arms come up. Okay. Get these all ready to go, and then we'll talk about them. Alright, the domain is all real numbers because we're allowed to plug in any value for x, and the range is just going to be all positive numbers, 0 and above, because it's all above the x-axis. So the graph of this thing consists of two separate quadratic functions. One of them is just the regular function. That would be the upward hump. From -2 to +4, we just use this regular quadratic function that opens down because everything's above the x-axis between -2 and +4. So when x is between -2 and +4, we just use this one. Okay, we just take whatever's inside the absolute value brackets, and that's our function. But outside of -2 and above +4, so if x is less than -2 or x is greater than +4, we have to use the graph of this thing that's reflected in the x-axis, so the negative version of this entire parabola, which of course we apply the negative sign to the whole thing, and it becomes x squared minus 2x minus 8, because we want to turn it into an upward opening parabola like this one, so that those things go up, those sort of arms go up like that rather than down, which they would with this one. Okay. So here's how we would write our piecewise function. We use this parabola, the downward opening one, between -2 and 4, so that's the hump, and we use this parabola, the negative version of it, so the upward opening one, if it's less than 2 or greater than 4, so we get those upward pointing arms. Okay, here's another your turn. Go ahead and give it a try, so hit pause. So this parabola is upward opening, so it'll go like this somehow, but this part below the x-axis is going to have to be reflected. So between your two intercepts, we are going to have to use the negative version of this function. Go ahead and give it a try. The answers will be here when you finish. So there you go. Hope you're feeling comfortable with that. We'll get some practice together, and I will see you in class.